Hi, I think you are doing well. So, if you can remember in our last video, what we did in our last video, we just uh, mm, redraw the model actually, right? So now we are going to start another video on PCF-based SPR temperature sensor actually. So, yeah, you can see that we are working on this paper, right? So we draw this model actually in COMSOL. Okay, this one is our model actually. Okay. Now what we have to do, we have to select materials from the materials. Okay. But before selecting material, what we have to do, we have to uh, get the material property of gold. They use gold actually, right? So we need material property of gold. We need material property of analytes. We need material property of silica. So the thing is, they are actually temperature dependent. Okay. So let me explain the thing how actually temperature sensor work. Okay. Okay. So okay. Uh, so this is the analyte. Okay. This is the analyte of temperature sensor. This is the silica. So, or the light guiding part, and this is the plasmonic material. This is gold here. Okay, and they are actually air holes. Okay, so in photonic crystal fiber, so how photonic crystal fiber work? In photonic crystal fiber, there are two different things. One is core and on another is cladding, right? So from the core will pass the light actually. So the refractive index of core is very high compared to this air hole. Okay, so the refractive index of air is actually 1. Okay, and the refractive index of core actually the silica or silicon dioxide, its refractive index is quite high. Okay, so the thing is what we have to do, and the refractive index of gold is vary with the wavelength. So the thing is, we'll and this surrounding and light is actually temperature dependent and light. Okay, so they are actually temperature dependent. Their refractive index vary with the temperature. So, for example, at the temperature of 0 degrees Celsius, 0 degrees Celsius, the temperature of this liquid is, for example, for example, sorry, sorry, at 0 degrees Celsius, the refractive index of this liquid is, for example, 1.31. Let's say 1.31. Okay. So then if we increase the temperature from 0 degrees Celsius to 20 degrees Celsius, then let's say it's a refractive index vary from 1.31 to 1. Let's say um, 36. Okay. So there is some sense of refractive index, right? So photonic crystal fiber based SPR sensor can detect the sense of refractive index. Okay. It's easy for it to detect the sense of refractive index. Okay, so if we can change the refractive index of this liquid, then it can sense the change of the refractive index, and from the change of refractive index, we can calculate the change of temperature. Okay, that's the thing. That's how the temperature sensor actually work. So we are putting here some temperature sensitive liquid. Okay, that's the thing here. Okay, and another thing I want to mention, the uh, silicon dioxide is not temperature insensitive. The refractive index of silicon dioxide is also dependent on wavelength as well as temperature. So we need a temperature dependent equation of for silicon dioxide as well. Okay, and we do have the equation of this analyte, temperature dependent analyte. Okay, so the name of the analyte maybe they mention. So we know actually maximum people use temperature sensitive liquid ethanol. Okay, maximum people actually use ethanol as a temperature dependent liquid. Okay, so I think you got it how actual temperature sensor work here. Okay, now what we need to mention those parameters for sensor. Then we have to calculate the diffraction index. Okay, so I already have the parameters of the temperature sensor. For that, what you have to do, you have to right click from parameters. You have to uh, get parameters from external. So from here, we have to load the file of parameters of material property. Okay, so from load, we have to load this parameters file. Okay. So this is all about the parameters of all the materials. Okay, so you have to write down this thing. So this is actually the temperature, variable temperature T is initially set it as 80 degrees Celsius, but we don't need to write the degree Celsius, as we have to write 80. Okay, and then from material, okay, you can see that this is the material property of gold. Okay, let me clear it. So this is the material property gold. So then to write down the material property, we need this all the parameters value, right? So for that, we have to write down the those variable name and their value actually. Okay, so this is actually omega. Its value is actually 2 pi 2 pi f actually. Omega is 2 pi f. So 2 pi into c is the velocity of light divided by L. L is the wavelength. Okay. Okay. This is the L is the wavelength. So we define it at the end. Okay. Then how we have to write down omega A. This the value of omega is actually 9.75. Then omega B, the value of omega B is actually 1.36 into 10 to the power 16 rate per second. And the unit is rate per second. Okay. Then omega C, its value is 1.45 into 10 to the power 14 rate per second. And then we'll get, then you have to write down the AU. Okay. AU actually, this is the EAU. Okay. This is actually EAU. Okay, this is actually EAU. From that, we have to calculate E1 and E2. Okay, so from EAU, we will get an imaginary, sorry, we will get a complex number. From the complex number, we have to, from the complex number, we have to separate the real part and the imaginary part. Okay, so so this is actually a complex number. From here, you can see that this is actually a complex number. So from here, we have to separate the real part. You have to write real EAU, then we will get the real part. Then imaginary EAU. From imaginary EAU, you will get the imaginary part of EAU. So they are actually permittivity of gold, but we have to calculate the refractive index of gold. Okay, we calculate the permittivity of gold till now. Then we have to calculate the refractive index of gold. So because in COMSOL we'll put it as a refractive index. Okay, so to calculate the refractive index from permittivity, this is the equation square root of u1 divided by 2 plus 0.5 into square root e1 to the power 2 plus e2 to the power 2. Okay, the value is actually 0.1441 okay. It's depending on wavelength. If you change the wavelength, then it will change actually. And then this is the real part of refractive index, and this is the imaginary of refractive index k au. Au is the gold, and k is the imaginary part. Okay, there n is the real part of refractive index, and au is the gold. Okay, so it is actually e2 divided by 2 into nau. Okay, real part of gold. Then then we have to define we calculate the refractive index of gold, real part and imaginary part. We calculate both the real part and imaginary part of gold. Now we have to calculate the refractive index of analyte. Okay, so to calculate the refractive index of analyte, this is the equation to calculate the refractive index of analyte. So we need T naught T, uh, DDT N, and N naught. Okay. So we already defined T, right? We already defined T. Now we need T naught, and sorry, this is Tn, and this is Na. Okay, this is actually the equation. This equation. Okay. Okay. So okay, we don't need to define the value n naught. We know the value of n naught is actually 1.44. So then we have to define plus dn into t minus t naught. Okay, so we got the material property of analyte as well. Now we have to we got the material property analyte of analyte. We know the refractive index of ER, right? So we don't need to define the refractive index of ER. So we calculate the refractive index of analyte. We calculate the refractive index of gold. Now we have to calculate the refractive index of silica. So to calculate the refractive index of silica, we have to define some uh, predefined material properties. So the refractive index of silica is depending on temperature. So its coefficient is depending on temperature. Okay. So this is the coefficient A naught. You have to write it 1.31552 plus 0.69075 into 10 to the power minus 6 into T. Okay, this way B is another coefficient, C is another coefficient, D is another coefficient, E is actually 100, and then this is the refractive index of silica. Here it's showing some problem actually, but it's not actually a problem. We got the value of silica actually, it's 1.4591. So it's not going to make any problem because the refractive index is fine. Okay. So this is the thing. And then this is the wavelength L is equal to 0.6 micrometer. Okay. So we defined all the material properties, all the parameters of material property. You can write it down from um, New York file. Okay. And then now we have to define the materials. Okay. From materials, what you have to do, you have to take a blank material. So we can define it as air. Okay, and then you have to deselect this on for and this on, this on, and this on, and sorry, as well as you have to deselect this one. Okay, so others are actually air, and the refractive index real part of air is actually 1, and imaginary part is 0. It's okay. So next we have to define blank material. So we have to uh, define it as um, and maybe gold. Okay, so This one is gold. So this thin layer is actually gold, right? So the real part of gold is actually NaU, and the imaginary part of gold is actually KaU, as we define in the parameter file. Okay. So then we have to select. We have to take another blank material. For that, we have to select this one. This one actually is silica. So SiO2 is actually silica. Okay. The refractive index, the real part of silica is actually what we defined. We defined it as Ns. Okay. So, or you can define it in SiO2. Okay. As your wish. No problem. So you have to copy it and then you can paste it here. Okay. And the imaginary part is actually 0. And then now we have to define the analyte. Okay. Okay, this is the analyte. Okay, this one will be analyte, and the boundary or PML layer is actually analyte. Okay, and the real part of analyte is actually Na, as we define in the material property, and imaginary part is 0. Okay. Oh, I forgot it. For silica, this one is also silica as they work actually, right? Okay. So see, this one is not silica, this one actually gold, and this one silica, this one silica. Okay, so we got all the, we define all the material properties for our temperature sensor. Now, what we have to do, we have to define, so material property is done, right? We did the geometry, we did the material property, and now from definition, what you have to do, you have to right click and select perfectly matched layer. This is actually PML layer. So this one actually perfectly matched layer. Okay. Sorry. So this one actually perfectly matched layer. So in perfectly matched layer, what you have to do, you have to select the type of the mesh layer is actually cylindrical. Okay. The type of the perfectly matched layer is actually cylindrical. You have to select it, and nothing else you have to do. Okay. Fine. Everything is done. Now, what we have to do, we have to, from electromagnetic wave frequency domain, you don't need to do anything. Okay, we have to, so here you can see that we are going to calculate full field, uh, scatter field as well as other field. Okay. And out of plane wave number is that is actually 0. Okay. And okay, everything is fine now. Now we can simulate the thing actually. We can simulate the file. It's completely okay if we simulate this file now. Okay. So now what we have to do, we have to, okay, but before simulation, we have to select the mesh. So here is the point. Mesh is very essential for PCF SPR sensor. Okay. So for mesh, you can select normal electromagnetic wave frequency domain as well as other mesh, or as well as you can select fine, extra fine, or other things. Okay, then build all. It may show some problem. Okay, So here you go. It's showing a error. I'm expecting that actually. So it's not a problem. So here in we select physics control mode mesh or physics control mesh. Select map automatically, but we don't need this map actually. We can delete the map. Okay, so we delete the map, and then from free triangular, you have to select this one as well. It's actually PML layer. Okay, then build on. Okay, then you can see that this is showing very good mesh actually. So it will take so much time to run the sim model. So what we can do, we can just select this two one, and then you can disable this to size, and then you can build on. Okay, so it's mass normal mesh. Okay, so that's why it will take less time. But if you take a very fine mesh, then it will show you very less simulation error. Okay, so when you are doing final model, then you have to select very fine mesh. Then it will show very less error. Okay. And another thing I can say you to get better results. So if from the rectangular, you have to right click and then select size. And from size, what you have to do, you have to select custom. From custom, you have to select maximum element size. So the maximum element size will be lambda or wavelength L divided by 5. So then well selected. This is the uh, very good mesh actually. So if you select this mesh, then it will not show any uh, simulation error actually. Okay. So this mesh is actually very fine. So for our case right now, we are not doing final nothing actually. That's why we don't need this thing. Okay. But this is actually recommended mesh actually for any kind of good model. Okay, so that's the thing. Okay, thank you. We done our mesh selection. Now, okay, so now what we can do, we can simulate the thing. So to simulate the thing, we from mode analysis, what you have to do, you have to select here. Sorry, you have to in mode analysis frequency, you have to select C constant divided by L. Okay, this is actually frequency, and design number of mode. You can select design number of mode. You can write down the design number of mode like 8 or 10 or something like that, and search for mode around shift. You have to select it as so. We are expecting that light will confine the middle of the fiber. This is actually silica. So we have to write down the refractive index of silica here. Okay, there's nothing. So we defined the refractive index of silica as NSI or 2, right? As I can remember. Okay, this is the thing. So now the model is ready to run. So we are going to run the model. So pray for me. Okay. Um, I'm expecting no error actually. So I think it will not show any error. Okay. convergence plot. So it's working perfectly. So here you can see that our model run perfectly. So you can search our mode actually. Okay, this is actually the type of mode actually we are seeing here. So to see this one actually Y polarized or X polarized, we have to say this one is Y polarized or X polarized. So to do that, we have to select arrow surface. From arrow surface, okay, this one actually Y polarized light. So yeah, and this one is actually X polarized light. Okay, yeah, this one actually yeah is PP mode. This one is PP mode. This one is PP mode. This is Y polarized light, and this is X polarized light, as you can see in the paper. Okay, okay, this is Y polarized light, and this is X polarized light. So in our work, it's also showing this kind of thing. So we simulate it, and then in our next video, what we'll do? Next video, we'll simulate. mm, cal- we will calculate this curve actually. So stay tuned. Thank you everyone. Okay, thank you. Goodbye. See you.